Good afternoon. This is CIVE 638, Sedimentation Engineering, and I'm Professor Victor Ponce, and this is the fall semester of the year 2022. And the subject today is introductory. We have a number of students. Some of them have not taken a class with me before. So the first thing I'm going to do is instruct all of you that have not had a class with me how to reach the material that we're going to be covering today. So in order to do that, I am going to go to the web. Hopefully it'll work fine. Okay, I'm on the web now. So now I'm going to share the screen, sure enough. So all of you now should be observing the red screen that is my website. Is that correct, Cassidy?
Yes, correct.
Okay, cool. So from here, this is my website where all the material for this class is contained. And the address is Ponce, that's my last name, ponce.sdsu.edu. That sits on one of the servers at school. Okay, so it's a university server, and that's the address you should first reach. Once you get there, the next step is to go to 610 over here. See the green block there, 610? Once you go to 610, directly you go to the class information. This is the class 638, so you go to 638 in there, and directly you go to the page, but it is protected. The username is CIVE638, lowercase altogether, and the password is Tuesday, lowercase altogether. I already typed that, so I'm in now. So we are in now. So I'm going to explain, for those of you that are new to this kind of teaching or my own teaching, I'm going to explain how we go about reaching the information and so forth. But first, we're going to go about explaining the front page in here. Welcome to CIVE 638, Sedimentation Engineering, Fall 2022. I remind all of you that we have a prerequisite stated in the catalog, and that is that all of you should have passed 444, which is applied hydraulics, with a grade of C or better. And it is my understanding that all of you have satisfied that prerequisite. If not, then we have to do something about it. In addition to that, there is it's not a prerequisite, but a very strong recommendation that all of you that have taken this class should have already taken open channel hydraulics, CIVE 530 in the notation of San Diego State, or else somewhere else if you come from some other country or some other state. Normally I would require 530, but my experience has been that it is a bit counterproductive to require graduate classes in order to take more graduate classes, because there's not enough planning that will allow for that. So therefore, I recommend for 530 highly. I also recommend, if you have not taken it, that you would consider signing up concurrently. So talk to me about it if you feel like you have space in your schedule this semester and you want to take it concurrently. It would be a lot better for all of us included, had you had 530 before, because this is an advanced class in fluid mechanics that deals with sedimentation. So we consider 530 to be, if not a prerequisite, absolute recommendation. Okay, in order to minimize the problems that some of you may have this semester in the issue of assimilating material for which you are not prepared, I have given you some help. I have posted on this site here my open channel hydraulics book. So I'm going to make this available for all of you, freely of course, because it's online, so that you can refer to the various chapters as the case may be as I talk about it. For instance, I talk about initiation of motion. And in this chapter 6 of my open channel hydraulics book, I have treated initiation of motion extensively. Okay, So that's one thing. The calendar, it's over here. I don't need to read it for you. You can read it on your own. But basically, we got 6 weeks of importance. Right now, week is week number 1. We have week number 6 where you have select a project. And I'll talk about that briefly later. Week number 6, select the project. Notice that it says Tuesday, 220927. What does that mean? 1730. It means year 22, September is 09, and 27 is the 27th of September. I don't do the normal thing people do it. Like they say, September 27, 2022. No, I do it this way because I've been on the web for almost 25 years, and I know this helps me to keep track of the stuff I do. So it's for my own orderly finding of files over the years. We have a ton of files, certainly more than 10,000, if not 20,000 files out there on this site, as you will eventually make sure you realize that that is in fact. We've been doing this for 24 years exactly, since the year 1999 when we got on the web. Okay, so week 9 is the midterm. Week 11, preliminary oral presentations. So the papers that you're going to write require in 2 presentations, a preliminary on week 11 and a final on week 16. So you choose your topic up to week 6, then you have 5 weeks to prepare it, 20-30%, and then 5 more weeks to finish it up 100% with the writing of a report. So that's the preliminary and the final oral presentations. The preliminary presentation is 7.5 minutes and the final 15 minutes. You, of course, are graded on everything, on the presentation of the report, on the presentation, on everything. I grade on everything. And they assign a final grade for the work that you're going to do. The project requires a report, which is due on week 16 at a certain date specified there. And finally, the final exam on week 17, according to the schedule, already been posted. I don't change that. Actually, final exams should not be changed because they create havoc in the rest of the schedule. My office hours. The preferred way to reach Dr. Ponce or Professor Ponce is via the course email. The specific course email for this course is called ponce638.opal@gmail.com. Why do I do that? Because from my experience, I have a lot of traffic with the students. And I don't want to have only one email or one personal email. Worse, that would be worse. Confuse the whole thing. So I have several emails. I actually have 4 or 5 emails that I actively work on. The email, if you want to talk to me, you'd have to talk to me through the Opal email. Why Opal? Because that's the name I gave it to distinguish it. Those of you that are taking 634 would notice that the name out there is not Opal, it's Jade. Okay, so Ponce638 Opal is the email for this class. Furthermore, I have scheduled or will schedule 3 20-minute virtual meeting slots for consultation individually with all of you or any of you. A, B, and C. A is at 19 right after class, B 1920 and C 1940. For 20 minutes, I will, via Zoom, I will meet with you individually to answer your questions or prepare you for your, whatever dealing you want to have that has to do with the class, with the subject related to the class. I am freely available, not freely, but I'm available to you. So it's up to you to schedule these slots up to 48 hours in advance. Grading policy. Homework set, 20%. Assignment set, 20%. Midterm, 20%. Project, 20%. Final, 20%. So you have 5 grades, basically. The homework set is 7 homework. And the assignment set, I believe, is 12. So the collection of all the homework is one grade. The collection of all assignments is 1 grade. Listen to this because it's important. A record of perfect attendance will earn a bonus of 1/3 letter grade. In other words, if you earn a B+ and you had perfect attendance according to my record, your grade will be automatically raised to A-. You have to be on my record. In other words, if you're late to class, right now I have 3, 6, 9, 11 people, I believe. 5, yeah. So I'm still missing 3 that haven't shown up or are there and are not there yet or haven't caught my attention yet. But it is to your advantage to make sure that if you come in late, after I take attendance, did you make sure that you call it to my attention? I'm here, Professor Ponce, please put me as present. Within reason, of course. I wouldn't want you to show up 30 minutes or 40 minutes later. If you show up maybe 5 minutes later, then I will take it. You know, that's fine.
Professor?
Yes.
My name is John Isha. I was like 3 minutes late.
Who are you?
John Isha?
John Isho. Okay, thank you, John. Anybody else out there that has come in late? I put you on, John. I'll put you on. I already wrote
Thank you.
it down.
I have a question regarding that policy. There's no leeway on like even one excuse. I mean, stuff happens and I don't.
I didn't understand what you were saying. Who's this?
There's Margot. So there's no leeway on that perfect attendance. Like if we tell you something came up early on in the day or
No,
something.
the leeway is that if you are sick, you tell me you're sick and you show it to me and I'll that will be leeway.
Okay.
Any other attendance, it's
Hello, Professor. This is
not
Chandra
attendance.
Raju.
I mean, you didn't show up. I mean, okay.
Got it.
The attendance for leeway for attendance is if you're sick. Okay. Virtual attendance to class is required. More than 2 unexcused absences. In other words, if you don't show up more than 2 times, then I will make sure that you somehow get a penalty for it. More than 2 times unexcused. Remember, I keep very good track of who's here and who's not here. Okay? So that's basically it as far as that is concerned.
Professor, my name is Jansi and I was like 2 to 3 minutes late for the class.
What is your name again?
Jansi.
Your last name only. Jansi.
Yeah, Gadi Raju, yeah.
Yeah, you were talking about Jansi was your first name, right?
Yeah, that is right.
Okay, you need to talk in terms of your last name. Gadi Raju.
Yeah, that's right.
That's it. You're right. I got you.
Thank
So
you.
right now I'm missing only one. I'm missing only one, and that's my grad column.
I'm here, Professor.
Oh, you're here?
Yeah.
You were able to make it. Congratulations.
Thank you very much.
You said, okay, so I have a full house here.
I think we might have to talk after class to figure out
Exactly what was going on. Okay, we'll do that. No problem.
Thank you very much.
Okay, things do happen, you know.
Thank you.
I have a full house right now. That's good. That's good. So for those of you that came in a little bit late, I've been going over what we're going to be doing this semester. If you felt you missed something, you can either ask me afterwards or ask any of your classmates. It's probably better at this point in time to ask me afterwards, after class. You either call me or not call me, send me an email, and I'll explain everything to you again, repeat it for you, okay? But at this point, we are in the grading policy. Attendance we already covered. Term project. The term project will consist of individual work on a topic selected from a suggested list, mutually agreed with the instructor. The report should be of professional quality. Its length should not exceed 15 pages. 15 pages, not more than 15 pages. I don't want 17 or 20 pages. I don't want to read a huge report. 15 pages should be, if you can't make it on 15 pages, you won't be able to make it. Text should be double-spaced, require 2 oral presentations. Use a professional presentation tool. This is a virtual class, and it should be stressed that the work is to be done individually, not only for homework, but also for exams. Instances of cheating will be dealt with as stated in the current SDSU catalog, which it's there for all of you to look at. Okay, so if there are no questions about this, I would like to proceed at this point. Questions? Okay, so we have the syllabus over here. That's the syllabus. The first part of the syllabus, syllabus part 1, which takes us through A, river mechanics, sediment production, channel morphology, then the midterm. And then right after that, we have the syllabus part 2, which comes after the midterm, sediment transport, reservoir sedimentation, bridge scour, sediment measurements. That covers the entire ground that we're going to be doing in this class. Homework instructions. This is very important. I urge you to read this carefully. Every homework and assignment must be submitted as one PDF file to my email. The name of the file should follow this format very carefully. This instruction should be strictly followed. I don't want PDF files from John Doe that is in any format that he or she wishes to do. It has to be this format so that I can put all of them in one file and make sure that I have all of you in a consistent way. So CIVE 638 and your last name, and then it says homework 01 or homework 02. There's 7 homeworks, I already told you. Or assignment 01, 03, 05, up to 12 assignments. The PDF should be clearly readable when printed under normal conditions. In the past, I've had people that send me their PDF and I can't read it, or I have a lot of trouble reading it. I don't want that to happen again. So files that cannot be read readily will be returned without grading. The material should be neatly presented in sequential order, easy to follow, with answers enclosed within a box. I understand you're all graduate students, and graduate students are a bunch really kind of separated from undergrads. You know what I mean. You're here because you have an objective to get better at what you do so that you can be better for yourself and for your family, and so forth. So, so neatly presented is very important. A failure to comply with these instructions will result in a grade penalty. All homework will be emailed to the course email, which is the OPAL email, no later than 22 hours on the posted due date. And the due date is posted. Okay, we got in here the homework. Homework 1, 2, 3, you can read the homework. You don't have to do it at this point because there is an assigned date and a due date. For instance, for homework 1, this is homework 1. It's got 4 problems in there. And it starts on 9/1. That means that's a week from today, and it goes to 9/15. I've given you 2 weeks to do this homework. There must be something in there. Actually, it's kind of a bit complicated, so I've thought I will give you some time. Homework 2, homework 3, and so on and so forth. Those are a green color means go and do. A red color is stop, right? So that is for the homework. And for the assignments, we have all these assignments. How many? There's 12 assignments. These assignments vary from simple essays to derivations, like derive equation 13.2, or problems, small problems, short problems. These are not long problems like the homework. These are short problems designed to have you maybe spend at most an hour on it, I would say, on these assignments. In the homework, you probably have to spend 3 hours. In the assignments, 1 hour. So it's a different kind of stuff. That's basically it. We've done this for a couple of years now. It has worked really well. Okay, that's the assignments. And the videos. We have a whole bunch of video. We are, as you know, you probably know, Dr. Video. They don't call me that, but I do have a lot of videos. So I'm going to have you look at the videos. I'm not going to be showing you every video that there is to be shown. Because if I did that, we will occupy the entire class. And that is not my objective. I will show you a few, though. Particularly today, since we're starting the class, I want to show you graphically what we are up against, or rather what we're getting into by choosing this subject of sedimentation engineering. So that's the today we're going to watch a couple or 3 videos if time permits. The projects. These are the projects as currently stands. Since I have, let me say this, since I have 14 students, I certainly was not expecting that number. Usually we have 8 or 10 students. So what I'm going to do in the next couple of days, if you allow me to do that, if you bear with me, I'm going to add a few subjects in here just to make sure that there's you have a little leeway in the choosing, because as it is, we got 14 students and 20 subjects. So there's not a whole lot of room for wiggling in there. So I may add 3 or 4 more, depends on how creative I get in the next couple of days, because it requires some thinking to create these projects so that they are not only good projects for you, but they're also doable. They're not too difficult or too easy, for that matter. Okay? Well, give me a couple of days to finish this list, because I certainly was not expecting to get 14 students. And finally, the photos. And I'm going to start with the photos today, right now. But before I do that, do I have any questions about so far, what I have said so far? Okay, let me proceed then. We have an hour, a little bit less than an hour. That's good. I posted these photos today because the subject matter that we are about to get into is extremely important. It's a part of hydraulic engineering. Hydrologic engineering is kind of related to hydraulic engineering. I guess one could say is within the other. In reality, the difference between hydraulics and hydrology, I already talked about that yesterday. Hydrology deals with the rain and where it goes. And hydraulics deals with the water that has accumulated after the rain and what is it going to do to the structures. Because we're engineers and we're about to design structures and they should be stable, right? The stability of the structures is important in hydraulics. But that stability could not be calculated unless you knew the quantity of water, which is determined by the hydrology. But where does sedimentation come in? Well, the issue is that water is never alone. You can never have in nature pure H2O. It's impossible. Why? Because H2O has the capability to pick up stuff, physically and chemically, both chemically and physically. It always has a tendency to pick up stuff. It either picks up dissolved solids or suspended solids, or even humic substances that may be around. There are rivers in the world that are full of humic substances, and I'll have a chance to briefly talk about that a little bit later on. So it's an extremely important subject. When a story, interesting story that relates to the subject, when the son of Einstein, Hans Einstein, was the son of Albert, in 1928, he had been practicing in civil engineering, and he had been doing steel design. And for whatever reason, I wasn't there, of course, 1928. I wasn't even born. For whatever reason, he didn't like the field. So he wanted to get into something else within the field. Within 5 years, people can do that. I mean, if you're going to change, you better change as soon as you can, okay? But you can change. People have changed. So fields like from hydraulics to structures, vice versa, soils, etc. So he wanted to change, and he asked his dad what what his dad suggested that he should do. And his dad, by the way, this is a lucky break. His dad had been asked 2 years earlier to give a lecture on any subject he wanted to give, because he was Einstein, okay, Albert Einstein. And he said, I'm going to be talking about meanders. Meanders has nothing to do with nuclear energy, but the elder Einstein was fascinated with meanders, and he gave a lecture, a famous lecture, which, by the way, I'm going to show you the lecture, Einstein's lecture, because it's written everywhere, okay? So the elder Einstein told his son at the time, why don't you get into sedimentation? It's a field, it's a new field, and hardly anybody knows anything about it. So he did. And subsequently, he went into the Swiss Federal Polytechnic, which is one of the best schools and technical schools in Switzerland. And then eventually they landed here in the United States. The elder Einstein and also the young Einstein. Eventually he became a professor over at the University of California, Berkeley. I believe that was in 1950. I'm talking about the son now, not the father. And from 1950 to 1973 or 75, when he passed away, he taught sedimentation engineering at the University of Cal, Berkeley. He may not have called it sedimentation engineering, because at the time it was called something else, like sediment problems and this and this and that. But in 1975, Professor Bononi of Caltech edited the book called the manual that ASCE put together. In the early 70s, there was a group of ASCE people that got together to write the manual, the ASCE Sedimentation Engineering Manual. So that is that constitutes the birth of the field, sedimentation engineering, 1975. Subsequently, Marcelo Garcia and his associates back in the year, I believe in the year 2008, wrote the second edition of sedimentation engineering, presumably more updated because it was done in the 2008. And Vanoni's book was dated 1975. Unfortunately, in my opinion, the book is not very selective. It ends up being twice or three times as heavy as the previous book. As a result of that, ASCE has not given up on the first edition. So if you want to buy the Sedimentation Engineering Manual from ASCE, and I recommend that you should if you want to get into this field, ASCE asks you want number one or number two or both. They'll sell you both for a reduced price. As a matter of fact, roughly on the order of $200. For $200, you can get both books, good books on the subject from ASCE. Obviously, I cannot teach with the Sedimentation Engineering Marcelo Garcia's book because it will never end. It's so thick and so heavy. What we're doing in here is a show, basically, to show you what things are out there in this field. It's a fascinating field. Not too many people get into it. You are, in some sense, should I say lucky? In some sense, lucky that you have a chance to get into this field early in the game, so to speak. And for myself, and I practiced in this area for many, many years. When I get back to Colorado State in the year 1973 to pursue a doctorate degree, because I wanted to go into academic field, into teaching and research, I signed up with Professor Simons's program. And his program was, well, he was recognized as one of the leaders, world leaders in the field of sedimentation engineering. So I felt that if I went under his, so to speak, tutelage, if he was my professor, I was going to benefit. And sure enough, I did. Daryl Simons was basically my mentor, one of my mentors. I had several. And eventually, obviously, he passed away, I believe, in the year 2005, at the age of 80-something, 80-plus years. A great guy. And I'm going to be mentioning in this course many of the works of Professor Simons that have formed my thinking, as a matter of fact, as a student of Professor Simons. So that's basically it. So what I want to do now, before I get started here with the syllabus, is show you a few photos of my collection so that you can see what kinds of problems could we get into if we're lucky and determined enough to get into this field and make something out of it, meaning get the jobs that will allow you to have the experience, and over the course of 20, 30 years, call yourself a sedimentation engineer. Not unlike Professor Einstein, Hans Einstein of Berkeley, and many others, Professor Daryl Simons, and many others. It is, though, I should tell you from the beginning, a small group in the hydraulics area. Not everybody that is a hydraulic engineer can claim to be a sedimentation engineer. And with that, I'm going to show you a bunch of these pictures. I'm going to spend more time in some of them because I know more and they're more interesting from our standpoint of finding out what exactly is it that we're getting into from a practical standpoint. We're going to be looking at a lot of equations, but then the question is, for a lot of people, is how am I going to use this? Is this something I could make a career of, make money, get a salary of? And of course, certainly that is the case. In here we have the Orgar Vein and the Metica River, Meta, Colombia. I happen to be a friend of Carlos Rodriguez, who has a company. He owns a company in Colombia, in Bogota, Colombia. And he does this for a living. After he was a classmate when I was at Colorado State in the early 70s. And he subsequently got into Colombia and founded this firm. I think it's called Hydroconsult. In Spanish, it would be Hidroconsulta. And he has consulted, I believe he recently retired, almost at the age of 80. I think he's 2 or 3 years older than I am, so he would be 78. And what did he do for the last 25 years? He did these veins that were designed by Professor Odgaard. He took the technology that Odgaard out of University of Iowa, had developed over the years, over the 80s and 90s, in order to hammer these veins on certain rivers so that they would be able to control the meandering. That's what this does, control the meandering. You're seeing in here one of them. They're about 10 foot long and about 8 to 10 foot deep, so they're hammered into, as if it were piles, as if it were longitudinal piles. They're hammered into the river at certain locations in certain quantity. I believe in these projects, usually they have 80 or 100 of these veins in a certain location. The objective is to avoid that the river should meander. Now, obviously, that's a losing game because the river is going to meander no matter what. So what our friend Carlos has done in here is stop the process temporarily. Temporarily means, if he's lucky, 5 to 10 years, maybe 20. But he cannot stop it forever. Forever is a very strong word. Forever would be like 5 generations down the road. God knows what could happen. What could happen? Who cares anyway, right? But that's the point. As a matter of fact, I can tell you off the bat that about 5 years ago, Carlos had put together about 18 to 20 of these projects in various rivers in Colombia. And one of them failed all of a sudden. He had to go on TV to explain the reasons and so on and so forth. I say this because it goes on to prove, to show in fact, that the projects that we do have a life which could be calculated, but it is only a rough estimate. In his case, he had done 20 projects and one of them failed. Failed meaning the veins were gone. The flood came over and took the veins with them, and God knows where they went, okay? So one failure, 20 successes, I guess no big deal. He continues to do this. Why would society want to stop these meanders from moving? Typically because somebody in the past has put a road right next to the river. Very typical. And the river is trying to change and meander and is going to take over the road. Since we don't want the road to change, or we don't want to reroute the alignment and so forth, we fight it. Society fights it. We hire the people that can do this, and we let it go that way. By the way, my friend Carlos, he's very well off. He became very well off because this stuff in here is not only consulting, it is also construction. And there's a lot, excuse me for saying this, but there's a lot more money in construction. So the gentleman is very well off. This is a good example of what is the difference between hydraulics and hydrology. Is the river hydraulics or is it hydrology? Actually, it is both. This is the Rachichola Creek in Lambayeque, Peru. Back in the year 2008, we had a project over there for a hydrology project, of which we talk about briefly in our other class 634. And in here, as you can see, we have these huge sediments. Yes, these are huge boulders, about 3-4 feet diameter. What are they doing there? Very simple. They are resting. They're resting there, waiting for the next flood. What's going to happen in the next flood? They're going to be taken up and moved downstream. Where are they going? They are going to disintegrate as they move downstream due to the force of the phenomenon and so forth. How do we know that? Because downstream, 20, 30 kilometers downstream, we don't see these rocks. And there's no reason to believe that somebody took them. They're too heavy. So they disintegrated totally, and we know that to be the case. So as you can see, this is the beginning of our understanding of why are we studying this. For one thing, the friction. For another thing, the stages, the calculation. This is a tough calculation. What manning are you going to use in there? That's a tough question. What fruit number is it? We don't know. That depends on where you are within the cross section, right? So as you can see, the difficulties of having to deal with this real world, real life situations. What is this? This is the upstream, that is the tail of the Tinajones Reservoir in Peru. the tail. Every reservoir has a tail, and the tail is full of sediment. In this case, this sediment is so good that it's serving as grazing area. When I was there, I saw many sheep out there. There are people out there, farmers and so forth, are raising sheep in the tail of the reservoir. They rented or leased this from the government because the government has it in there. They've had it for 20, 30, 40 years. This reservoir's been up for 40 years. So that's the river that goes into the reservoir, and it's been depositing this delta of sediment that's coming from upstream. So deposition is also very important, not only erosion. Our field is divided into three major areas: erosion, transport, and deposition. And there are three completely different areas or fields. This is fascinating. Back in the early 2000s, we did a study on the El Barbon Creek in Mexico, in east of Ensenada. And the issue was, where's the sand? Because the sand mining companies wanted to find out where the sand was so they could claim it. They could claim it, say, for 40, 50 years. I'm going to claim all the sand. So myself and a student of ours at that time, Mr. Erkan, who did a master's thesis with me in the year, I believe it was 2001, we came up with a profile, and we showed the profile to the people and told them that the sand was going to be over here, El Real del Castillo Viejo, and a little bit over here, and a whole lot over here, and over here. In other words, in the flat areas is where the sand was going to be. In the steep areas like here, there's no sand. It's all rock. It suffices to say that if the flow is very fast, no sand is going to hold on to the rock, right? But in here, the flow kind of reduces. Due to the profile, it reduces, and it allows this very long, this is, I don't know, 10 miles or so. No, 10 kilometers. About 10 kilometers. There's a lot of sand out there. Not only is it a lot of sand, but you can mine it and wait 20 years and it'll be replenished. Then when you have a hole in there, the next time the sand comes, it'll fill the hole and then you're ready to go again. Why sand? Why is sand so important? Well, suffice it to say at this point, without making it too long a conversation, that sand at that time, about 20 years ago, was for all practical, sand mining was for all practical purposes not allowed in California. So we needed sand in here, and the only way we could get out of the bind is to go out there and find it in Mexico. So the business of sand mining in Mexico, in Baja California, mushroomed in the late 90s and 2000s. And a lot of that sand that we are using, we had used here or have been using here, both in San Diego as well as in all Southern California, has originated in these two. There's two rivers, Las Palmas and this El Barbon Guadalupe. So as you can see, it's tied to the economics, it's tied to the geology. Why here? Because we have a phenomenon which we call uplift. There's uplift in here, uplift in here, and uplift in here. Uplift means the ground is going up and is providing these nuances in the profile that allow the accumulation of sand in certain places. So as you can see, combination of sediment transport, sediment deposition, geology, and all kinds of stuff. When we presented this chart, it was a surprise because most people didn't realize that was the process. But we understood both the geology as well as the sediment transport. This is a fascinating picture. Deposition of large boulders on the sides of the Snake River Canyon in Idaho, downstream of Pocatello. Why is it strange? Because these are huge boulders. Why? What are they doing there? You must have had a huge flood in order to move these huge boulders. Otherwise, they would not be there, right? Another case of the same picture. This is Google Earth, by the way. The same boulder. How do you get these huge boulders about 10 foot wide, or at least 8 foot wide, on the hills? On the hill, how did they get to be, how did they climb on the hill? And the answer is no, they didn't. They were deposited there by a huge flood. So where is this, how big was this huge flood? We happen to know now that it was extremely huge. It happened 14,000 years ago in this particular region, and I'll explain later on why. So these are two pictures that we were able to take from Google Earth. I actually never went out there. We wanted to, but we never had the time or whatever, the luck or to head out there and inspect the site personally. I wanted to do that, but I have not done it. But Google helps you. Google Earth helps you. Birds Point, New Madrid floodway, eastern Missouri, immediately after the Mississippi-Ohio River flood. Talk about sedimentation, sedimentation engineering. When the Mississippi, we know, and this is the confluence of the Mississippi and the Ohio. I'm sorry, not the Ohio. This is the Ohio, and this is, I believe, the Mississippi, right? And then the Missouri comes a little further up. I think I'm right in there. At any rate, in here, the confluence of the Ohio and the Mississippi, we get this issue in here. That's the Mississippi River. The Mississippi River, okay? And the Mississippi River has a way of flooding, of wanting to flood. Why? That's in nature. Nature created this huge valley, and it didn't do it without water. There was a whole lot of water here. We're talking here millions of years, okay? At least 2 or 3 million years of the formation of the Mississippi River Valley. So the Mississippi brings a lot of sediment and a lot of water. A lot of water and a lot of sediment with it. Okay, so the issue here was how to protect the city of Nashville from a flood. And in the year 1837, I believe, no, 1937. In the year 1937, the Army Corps of Engineers, which is in charge here as far as the management of the Mississippi, they decided to do a floodway. They did this floodway. This floodway has an opening here. Okay, it's protected. If there's no flood, the floodway is not being operated. And then if there's a flood, then what they do is they produce what they call a fuse or a levee breach, purpose levee breach, in order to get the floodway to operate. And that's exactly what happened in May 2011. The floodway operated, and I was lucky that I was online a few days later, and I was able to take this picture. I did not take this picture. Somebody else took it. But this is the floodway after a few days after it had allowed the water to run into the floodway, thereby releasing the pressure downstream and not flooding Nashville. I have a video on this, which I hope to show you today sometime. As you can see, very practical stuff. This is agriculture on the slopes. If we do agriculture on the slopes, it's very important to make sure that we're not moving the sediment away. And apparently these people are doing the right thing. Exactly how, I do not know, but they're doing it. Same in here. I was very much impressed. These are hill slopes on the Moyan watershed in Cajamarca, Peru. As you can see, 20, 30%, if not more, steep. And yet, they're fine. If they were not fine, they would have already developed what we call gullies, and we will talk about gullies later on. I was talking about humic substances earlier. Well, here it is, the example of what I was talking about here. This is the confluence of the Rio Negro and the Amazon. The Amazon is the brown one, which comes from the hills, bringing the sediment. The Rio Negro comes from the northern plains of Brazil, in the Pará region, Pará state, where there is no sediment in there. So there's no sediment, but there's a lot of vegetation. So the vegetation has produced, the decay of the vegetation has produced the humic substances, which are all over, and produce the characteristic blackness of the water, of the river water. So in here, this place is called the Meeting of the Waters in Manaus, Brazil, where the Amazon meets the Negro and eventually swallows it because the Amazon is a lot larger at this point. Landscape in the Piraí River, Bolivia. In 1989, I was in Bolivia on a study of sediment routing, sediment transport, sediment routing. As a matter of fact, we developed a model over there, a computational model to do this kind of stuff. That's why they hired me to do a computational model. We went upstream and we wanted to find out where the sources of the sediment were. And I was able to luckily get into this place where we found the sources of the sediment. I'm not exactly sure if this is natural or anthropogenic. I have a feeling that it's maybe both. One would have to do a study over here to determine based on stories from the local people, if this thing, as it shows in there, always existed, at least in the memory that we can rely upon, or did it just develop in the last few years? And typically, if there's accelerated erosion, it will be accelerated. It will develop quickly within a few years. So this is one extreme example of accelerated, perhaps anthropogenic erosion. Likewise in here, this is in the Mixteca Alta, also gullies. These are the famous or infamous gullies that we have talked about. Another gully, this is in Northern California. The people out there over the last 20 years, 25, 30 years, have actually engaged in trying to manage and control these gullies. It's a difficult proposition, but it is being done. It is being done. I can tell you, and we'll share some information on that later on. This is the Mojave River at a place where it breached its ford. This is interesting. The highway department over in this place, I guess you would say the California DOT, did not feel necessary for them to do a bridge over here because it was a wide river. It was the Mojave, and it was the traffic didn't justify it. You know, a bridge has to be justified by the amount of traffic. So in this case, they didn't do a bridge, they did a ford. And we'll talk about fords later on. But the ford was swallowed by the huge, I believe it was 2004, flood. This is the flood of the Succiata River, the border between Mexico and Guatemala. It created a bluff in there. The bluff wasn't there. And all of a sudden it was created. The people in Guatemala, the owners of land on the other side of the border from Mexico, must have lost some land in there. Some land went with the river into the ocean. This is what happens when meandering takes place. The meandering will break and will kick the dirt or the soil around, and eventually the soil gets to the ocean with the next flood. There's always a flood coming up. Okay, so that's bank erosion in the Rio Negro, border between Brazil and Paraguay. I was there in 1992 because we had a study in the upper Paraguay, and I wanted to make sure that I knew everything from the top to the bottom, and I did that. I traveled all the way. I'm very knowledgeable with the upper Paraguay, all the way from the top to the bottom. This is at the bottom, at the further southernmost point of the upper Paraguay, the confluence with the Rio Negro, where there's a lot of bank erosion. You can even see this stuff in the flying over with Google Earth. This one is not too important. This is another repeat in here. This is interesting. Large beaver dam. When we did the study back in the year 89, 90, more than 30 years ago, we were charged with finding ways that water could be retained, either naturally or artificially, in the upstream of the watersheds. And we went out there, and again, luckily, we found this huge beaver dam. And they say that the beavers are very good hydraulic engineers. I can tell you that I did not see any leak, even though you can see the structure and the material. The beavers do this. The reason why they do this, I think it's been documented. They do that for protection and safety from predators. They have a lot of predators out there. And they're beavers that are small, so they protect themselves because they're amphibious. They can go underground or underwater. The predators cannot go underwater, so they protect themselves that way. But one thing is very important to consider, at least from our standpoint, and it is the being good hydraulic engineers, because there are no leaks to the dam. They're not good hydrologic engineers. They cannot calculate the frequency of the floods. So if there's a huge flood out there, the entire dam will fail. And when it fails, the other dams downstream will also fail in tandem, like a domino effect. So that happens. This is a gully developed during 1992 flood in Sierra Juarez. He's one of our students, Mr. Shetty, year 2002, I believe. He was one of our students. Standing in front of a gully that prior to the flood, 1992, did not exist. 1992 was a El Nino year. And the El Nino year affects everything from Peru throughout California and even to Japan, because it is a global Pacific atmospheric phenomenon. And that's basically it. That's basically it. I'll get back to this. This is interesting and important. Constructed micro relief to control erosion in the Wasatch Mountains. Remember, I said that there's erosion, transportation, and deposition. And we as engineers, as sedimentation engineers, study all of them. Because one of the cause, the other one is the continuation, and then there's the effect. And in here, we have people from the WPA constructing erosion control features in the Wasatch Mountains in Utah. Very successfully, they did these reservoirs, very small reservoirs, as you can see, to hold on to the water. Because without the water ponding in these very small ponds, it was going to rush down. And prior to this being constructed in the early 30s, I think it was in 1930, that they had this huge debris flow which covered the mouth of the basin with about 10 or 15 feet of dirt. And that was terrible. People may have even gotten killed at the time. So this, we call this micro relief, solve the problem in the Wasatch Mountains. And so on and so forth. I'm going to finish there. These are all repetitions. These are all repetitions. Oh, and finally, I'm going to get in here. Upper Paraguay River Fechó dos Morros, which means it's Portuguese for closing of the hills. What actually happened here was that there was an uplift event when many years ago, I'm guessing 4 or 5 million years ago, which raised the surface of the land was raised 40 meters. And by doing that, because the area is very flat, it created a pond in the upstream. And that pond became, in time, the largest wetland in the world, the Upper Paraguay wetland, which is considered to be, like I said, in size, the largest wetland. It's something on the order of 140,000 square kilometers. It's about 60 or 70,000 square miles. It's the largest, by far, wetland in the world. Now, wetlands are an interesting feature of nature in human society because in the past, we used to disregard wetlands and consider them to be not important. But since 1990, after the Wetlands Act in the United States, wetland protection has taken over, not only in the US, but around the world. So now we protect wetlands. We used to destroy them, get rid of them, because we thought that they were not useful for human beings. But now the environmental problems or environmental movement has set in, and now the tendency is to protect wetlands. So this wetland is now being protected. And I participated in a project in the year 1995 to protect this wetland. And that's why I became, actually, I had 2 projects over there, one in 79 and then in 1995. I do not believe we cover in this class, because this is surface water hydrology, but in environmental engineering, those of you that took environmental engineering, in environmental hydrology, those of you that took my class last year would probably remember what when I discussed the Upper Paraguay, because I do that in that class. Okay, so now at this point I'm going to finish in here, and I'm going to go back to the syllabus, and the syllabus sediment properties. Okay, I'm going to try to do as best I can in here. I've got 20 minutes with the actual subject matter. I spent a lot of time with the pictures, but I felt it was important to give you a feel, a raster field, not a vector field. What's the difference? Vector is what we're seeing here right now. These are all vectors. There's no pictures. And on the other demonstration that I just finished talking about, that was all mostly words, mostly pictures, not words. So that's the difference between vector and raster. And we believe that a combination of both is best, because the mind works better if you put them together. Sure. Like they say, show me with one picture, which is worth 1,000 words. Nevertheless, we're going to be looking now at the sediment properties. So this is part of my book, chapter 13 of my book. And by the way, I already said, and let me increase the size in here. I already said that the processes are production, transport, and deposition. And we're going to state that. We're going to talk about production, then we'll talk about transport, and then about deposition. Now, in reality, by the way, when you come down to actual practice, people have a tendency to specialize. And you'll have engineers that only deal with erosion, those that only deal with transport, and eventually those that perhaps only deal with deposition. That, of course, I think that is over-specialization. It is one sediment, and it's going from here to there by virtue of the laws of gravity. I can tell you that many of the engineers that I know, the hydraulic engineers that I know, they don't deal with production. They have a tendency to deal only with transport. They're busy with transport. They spend all their lives studying transport. So they didn't get too much to production. The issue of production of sediment is typically dealt with by the agricultural engineers, not the civil engineers. You know that there's a slight difference. And the deposition, well, the deposition is true hydraulic engineering too, but the deposition usually occurs in the deltas. In the deltas, the largest deltas are next to the ocean. So therefore, the ocean engineers perhaps are the ones that are more currently or more commonly dealing with the deposition problems. But having said that, I'm going to say that I consider all three of them parts of one thing, of the transport of the sediment. And I already said the sediment transports. Why? Because it's being disaggregated, and it has to transport because it rains. And it transports and it gets to the lower areas, which is the rivers, and eventually it gets to the ocean. If we don't stop the sediment, what happens is, if we stop the sediment and don't let it get to the ocean is going to be starved, and it will try to erode. And that has happened, by the way. And one of the criticisms which has been made against dams, against the construction of dams, is that they're starving the ocean for sediment, and the ocean is actually attacking the coasts. That's well said, but the alternative would be to get rid of all the dams, and we're not going to do that in the foreseeable future. We need the water. I mean, California has maybe 1,000 reservoirs. And if somebody came over and says, so you know what, these reservoirs are bad and we're not going to do them anymore, we're going to undo them. And that would basically mean that we would have to tell 20, 30, 50% of the people in California to go back to where they came from because there's no water. So far, that hasn't happened. It's politically something that, at this point, is unthinkable for us to think that we were going to get rid of the reservoirs. Suffice it to say at this point that we have gotten rid of some reservoirs, but a few, maybe a handful, not that many. Okay, and we are in the process perhaps of, if not continuing holding on to the reservoirs that we have some large reservoirs that provide water from the south, from the Southland. The water from us, for Southern California is coming from the Colorado River east and from the northern California, north. If it were not for the Colorado River, and which is bringing water from the east to all the way from Utah, as a matter of fact, and water coming from the north, we could not develop Southern California. We have been developing Southern California for the last 100 years because of that. The issue is, when will it stop? We don't know. There was a gentleman by the name of, I don't remember his name right now. He wrote a very good book called Cadillac Desert, which I recommend all of you that are interested in the politics of water and the issues of water in general to read that book. It's a very well-known book. I believe his name is Reisner, R-E-I-S-N-E-R. He basically said that the system was unsustainable, and I think he was correct. On the long term, he's correct. Interestingly, though, he kicked the bucket. He wrote the book, and then for some reason he died young, as a matter of fact. I don't believe Reisner was even 60 when he died. He wrote a great book, and then he passed away. Okay, he said the book says it correctly. It's just that in the speed or the earning or building California, in the race to build California over the last 100 years, most of us forgot that there's an issue of sustainability. Reisner brought it up, and he said, well, you know, this stuff is unsustainable. And yet, we still have not really come to grips with the fact that we are going to have to do something perhaps different in the future. But that is in the realm of politics. We're not here to talk about that. We're more concentrated on the sediment and how it moves and where it goes. One thing I should say at this point, though, is that there's a law in nature which kind of parallels the physical law, the mechanical law of Newton, that said action follows, or reaction follows action, and that everybody accepts. You cannot have a force applied without having an equal and contrary in direction force to it. Well, we can pursue that in the social realm of things, in saying that you can't do, or nothing could happen to you in a positive way without coming up with some negative to contend with. And that is the essence of what we call environmental impact. For instance, the environmental impact of a dam. The dam is going to collect the water. The water we need it because everybody showers every day. I shower every day. I don't know about you guys. Okay? There's a certain amount of water. Multiply that by all the population of San Diego, and that's a heck of a lot of water. Where's it coming from? It is actually being transported all the way from where it originates and where it is not used. Because if it were used where it originates, it would not come over here. That's simply said. The reason why it's over or surplus over in Northern California, and that's why it's being pumped all the way over here. Why surplus? Because you know what, and I'm going to tell you what, something you may not know, or it will open your eyes. But people talk fondly about water, but they prefer no water. If this were not the case, then we would not be living here in Southern California. Half of the population of California is in Southern California, or even more. Okay, we prefer the sun, and if there's a whole lot of sun, there's very little rain, and there's no rain, there's no water. Okay, so the issue is, and I think this issue has been brought out in many quarters, that every time we gain something, we're going to lose something, and there's nothing that we can do about it. We just, as engineers, we have to evaluate what the loss was. We've been trying to do that for the last 20, 30 years with the so-called environmental impact, of which I covered last year in the course Environmental Hydrology. But there's always an impact on anything we do, particularly with sediment. If we stop the sediment here, it will be picked up later downstream. If we increase the sediment here, it would not be increased downstream, and so on and so forth. And that's what happens with all our projects. So when we have a project, a hydraulic project, we should always either do or hire the expert in sedimentation that is going to tell us where the sediment is, how much is there, and where is it going to go in time and space. And that's what we're here to learn. Where is it going to go in time and space? The whys we already know. The sediment is being produced because the water has an intrinsic tendency to pick up stuff. If not by shear, by chemical action. The so-called dipole moment of the molecule of water, which we've studied in environmental hydrology. Okay, so sediment is going to be there. We can't get rid of it. We might as well live with it. And that's what we hopefully try to get by learning how to do it. Okay, sediment formation. The sediments are product of disintegration and decomposition of rocks. That is already easy to understand. Particle characteristics, the size. The size of the grains describe their properties. Among them are size, shape, specific weight, specific gravity, and fall velocity. The size, there's a classification which is given by AGU, I believe, American Geophysical Union, is this one over here. Classification of sediments. Very large boulders in millimeters, 4,000 millimeters, that's 4 meters. That's kind of similar to the one picture I showed you on the Rachichuela Creek in Peru, in northern Peru. Very large boulders, etc. Gravel, very coarse gravel, sand, very coarse sand, silt, coarse, and clay. So that's a standard definition of particle size, taken from the references, standard references, government references. Shape, the shape factors often used as an indicator of shape particle. I've actually have looked at this and never had a chance to practically use it, but we put it in here because it's part of all the manuals, the shape. The specific weight is something more important, specific weight and specific gravity. The specific weight of a sediment particle is its weight per unit volume. And the specific gravity of a sediment particle is the ratio of its weight to the weight of an equal volume of water. So specific gravity is 2.65 because of the fact that most sand, silt, and clay are made out of quartz or feldspar, which weighs 2.65 times heavier than water. There's some exceptions, but they're not very common. I would say largely 99% or even more of the specific weight is 2.65. It varies between 2.65 and 2.67 depending on who you call, who you talk to. As we say in there, magnetite, which is a specific kind of rock, would have a specific gravity all the way up to 5.18 because it has a lot of iron in there. And iron, you know, has a very high specific gravity as an element. The fall velocity. And here's what the plot thickens. Here we're going to get into fluid mechanics, by the way, because the issue of the pickup of the particle by entrainment of the flow is a fluid mechanics problem. It's a two-phase problem. It's not just water. It's water with sediment. So it's very complicated, very complex subject. Einstein recommended it to his son. He says, nobody's doing this. You're very smart. You're my son. You could do it. And he did it, actually. He did very well. Einstein, the son, was credited with developing the Einstein method. The Einstein method. Later, a few years later, Kolbe, working out of, I believe, USGS, the Geological Survey, developed a modified Einstein method. Suffice it to say that without Einstein, Kolbe would not have been able to develop his modified Einstein. He modified the Einstein method. It's basically the Einstein method that has been made somewhat easier to deal with and put in a step-by-step procedure. Because Einstein obviously never bothered to put his method on a step-by-step procedure. So modified Einstein, Kolbe, as a matter of fact, the developer of the modified Einstein, became very famous and very useful, by the way, because his method is up to this date still used by practicing engineers. It's the only method that gives you a complete assessment of the entire process of sediment transport, the amount of sediment transport. And I'll have a chance to extensively talk about that later on. So what is the fall velocity? The fall velocity can be expressed as follows. Equation 13.2. Where does this formula originate? Which is not simple, but it can be done. And I believe as part of the homework, I've asked you to derive this formula. How do we do this? Okay. The fall velocity of a particle derived from a balance of submerged weight and drag. So what the fall velocity is a terminal rate of settling. So it's a steady velocity. What happens is that when you drop a ball, a sphere or something, a particle, it will develop a speed and then will acquire a terminal velocity. So the terminal velocity is calculated by equating the submerged weight with the drag. And the submerged weight, we assume this to be a sphere, so we can figure out the volume of the sphere and the gravitational force and so forth. And the drag comes from the surface of the sphere. And the surface, as you know, we know the area of the surface and so forth, so we can do this calculation. For that purpose, the C sub D is the drag coefficient, and the C sub D, for your information, just to simplify things, I have defined here the definition between the shear stress and the drag coefficient. Rho is the density of water, and W is the fall velocity. So you ought to be able, by considering the weight, the submerged weight equal to the drag force, to derive this formula. And I've given you that as an exercise to do. Now, the drag coefficient is a function of the particle Reynolds number. Now, what is the Reynolds number? It's the number that was developed by Reynolds in England about maybe a couple hundred years ago. So this is a particle Reynolds number. It's not the Reynolds number of the flow, but a particle Reynolds number of sedimentation engineering. And that's equal to the fall velocity times the diameter over the kinematic viscosity in the proper units, because the Reynolds number is supposed to be a dimensionless value. Okay, so we substitute this for Reynolds numbers less than 0.1, the drag coefficient is equal to 24 over R, which is this line over here. It's in the laminar regime. This is the turbulent regime, and here the laminar regime. In the laminar regime, the drag coefficient could be expressed readily as a function of the Reynolds number here, And then when we substitute this into equation 13.2, and you can verify that for yourself, we get the W in here. 1 second. Where is it? Oh, here. We get 13.2 in there. Okay. That is Stokes Law. In other words, Stokes Law is the fall velocity under quiescent water for the laminar regime, not for the turbulent regime. If we wanted to do it for the turbulent regime, then we would have to get into this chart over here, into this chart, which has the shows the drag coefficient in terms of the Reynolds number. And it can be done. It can be done, as I said yesterday, you can do it in an Excel sheet, or you can use one of our calculators. It'll have to be an iterative process. And we have actually set up the iteration for you in a calculator here. As I say in here, in many applications, the drag coefficient is not known. In this case, an iterative solution is warranted. We assume a particle Reynolds number, and the drag coefficient is obtained from figure 13.1. In other words, from here. This is not an analytic function, but you can put this equation in the computer by making it a piecewise linear function. A whole bunch of dots following the curve will do it for you. And that's the way we do it all the time, by the way. When we don't have a function, we do a piecewise linear function. Okay, so we have a particle Reynolds number. The drag coefficient is obtained from figure 13.1 from here. Obtain the drag coefficient. Given a particle, assume particle Reynolds number, we get from the solid line the drag coefficient. We have the computer do it. Well, it can be done also by hand. Okay. Then from there we calculate a fall velocity and then a Reynolds number. And the iteration is continued until there's sufficient agreement between assume and calculate a Reynolds number. The procedure is illustrated by example 13.2. Same thing, diameter 0.1 and water temperature 20 Celsius, so we can calculate from here the kinematic viscosity, which varies with the temperature. As I say in here, step-by-step procedure, and then we go to the fall velocity. We go to the fall velocity in here. Test 220823, 1844, metric units, particle diameter 0.1 millimeters, and water temperature 20. Okay, so the fall velocity is 0.00767. In other words, 7 millimeters per second. That's the fall velocity of this particular problem. So I'm going to stop there. I intended to finish this section today, but I spent a lot of time with the figures, when I actually didn't show you at least a couple. I intended to show you a couple of the videos. So why don't we do this? This is what we're going to do. When I come back the next time, I am going to show you, I want you to see the last one, and I'll show the other two. So you see the last one, it's just kind of related, but not so much. I'll show the other two as we come in next time, Thursday, and then you can watch this on your own time. All three of them are examples of what we've been talking about here. I just pulled this today, as a matter of fact, of my large collection of movies that I have. I currently have about more than 1,000 videos out there. And we are, by the way, I might not have said this, but I'm in the process of videographing all our classes. The reason is because I want to leave this as my legacy, because some of you may know or may not know, but this is the last year, my last year of teaching at San Diego State University. So I'm going to record all the lectures and I'm going to put them in a file where people can access it for years to come. That doesn't mean that I am saying that you don't have to come to class, by the way. I'm just half joking on this. But you have a backup. In the case where you would have felt ill or could not attend for whatever reason, there's always going to be a backup to the lecture. With that, if there are no questions, I'm going to finish at this point. Questions?
Yeah, Professor, I do have a quick question, actually.
Sure.
So the email that we use to contact you is Ponce638, but the email for the homeworks is Ponce634.
No,
Because it's on, when I look at the web page for
if I
homework
made
assignment,
that, I made a mistake, and mistakes can be corrected.
yeah, on the instructions for homework, it has the 634 email.
Work instructions. Yeah, it's a mistake.
Okay,
It's a mistake. I can make mistakes. I'm not perfect. I make a
So-
mistake. I'll fix it in the next couple hours.
okay, so then so everything as far as homework assignments, the questions, all goes to the same email, the 638 one.
638. If you are, who is you? Oh, John?
Yeah.
Okay, you're not taking 634, so you don't have to worry about 64 at all.
Perfect.
Several of our group here are taking both, so they would have to sort it out. If they want to give a question on 638, they'll have to go to the 638 mail, right?
Yeah.
But you don't have
Yeah.
to do that. You only have one. And thank you for the warning. There's a mistake. I have to fix it. What happens is that sometimes you copy and you don't copy perfectly. Okay, fine.
Yeah, I
Thank you.
totally agree. Thanks
Okay.
for the clarification.
Okay. So I'm going to stop now, and I'll see you this Thursday at 5:30.